Hello everybody. In the last class we concluded the discussion of the induction machine, and we saw how important the induction machine was and the various applications the induction machines acting as a motor, acting as a generator, and the various other features of the induction motor like almost constant speed, the ability that we can control the speed with added electronics and things like that. So it's a very popular motor. Today we shall try to get a glimpse of another machine called the synchronous machine. So the synchronous machine, as the name suggests, the rotor shaft will rotate in synchronism with the rotating magnetic field. In the case of the induction machine, we had the rotor shaft rotating slightly slower than the rotating magnetic field by an amount called the slip. So therefore the shaft speed was always lesser than the synchronous speed. In the case of the synchronous machine, the shaft speed will always be in synchronism with the rotating magnetic field, and therefore the shaft rotates at the synchronous speed ns, which is equal to 120 f by p. Therefore, the synchronous motor is actually a constant speed motor if we keep the stator frequency constant. Synchronous motors, the synchronous machine also can act in both the ways. That is, you can have the power or the energy fed from the electrical domain and take the output energy or the output power from the mechanical domain, then it is called a synchronous motor. If we have the energy fed in from the mechanical domain and then take the energy out from the electrical domain, then it is called a synchronous generator or an alternator. So the synchronous motor behaves very similar to the way we discussed the concepts that we discussed in the case of the DC motor and DC generator. So in this class we shall get some insight. We will not go into too much of great details into the synchronous machine, but we will try to get a glimpse or insight into the concept of the working of the synchronous machine and try to see some of its important uses. In fact, the synchronous generator, that is the alternator, is one of the most widely used sources of power, sources of three-phase power that you get at the wall outlet. So almost all the generating sources at the generating stations, the shaft is turning an alternator which is going to give you a three-phase output. So synchronous machines are also pretty popular, but at a very higher rating compared to the induction machine. So today's topic is synchronous machine. So let us start with the synchronous motor first. The operation of the synchronous motor and the synchronous generator are exactly similar except for the power flow. Like in the DC generator and DC motor, you can use the same machine either way, both ways. See, the operation principle of the synchronous motor is pretty straightforward and simple. It is more on the principle of attraction, magnetic attraction. Magnetic attraction between poles, between unlike poles. Let us consider a stator and inside the stator let us have a rotor. Let us draw a salient pole rotor to understand the concept. So let me draw a rotor like that. This is called a salient pole rotor. And to the stator we shall connect the three-phase supply. So to the stator we give the three-phase supply as shown here. So we have the A, B and the C phases which are connected to the A, B and the C phase of the stator terminals. So this is the stator and the blue inner salient pole is the rotor. Okay. So let us say for the moment that we have some way energize this rotor, and this rotor is a magnetic rotor. That is, it is a magnetic rotor which has a north pole and a south pole. So the rotor is a magnetic rotor. It's a magnet which has two poles, north and south. Now the moment we give the three-phase AC supply to the stator, and the stator coils are wound 120 degrees mechanically spaced apart in space, then what should we get? We should get a rotating magnetic field, just like in the case of the induction motor. So we are giving three-phase supply to three coils of the stator which are 120 degrees mechanically spaced with respect to each other. Now this is going to produce a magnetic field, and I will put that one as an imaginary magnetic field in the shape of a dumbbell as shown here. So an imaginary magnetic field is produced. Let us say we have this which is rotating. And we have the dumbbell which is the imaginary magnetic field which is rotating at what speed? It is rotating at speed ns, which is given by 120 F stator by P, the number of poles per phase. Exactly same as the case of the induction motor. What is different is the rotor. The rotor is a magnet which has north and south poles. So therefore at a given instant, let us say this portion is south, this portion is north. Let us say the field which is rotating due to the excitation of the stator is having a north and the south pole like that. The rotor is also a magnet. It has its north and south pole. So the north pole is getting attracted to the south pole of the rotating magnetic field. The south pole is going to get attracted to the north pole of the rotating magnetic field. Now as the dumbbell, that is the stator generated magnetic field, is rotating, by magnetic attraction it is also going to pull the rotor poles along with that, and as a consequence the rotor is also going to rotate along with the stator magnetic field. So as the stator magnetic field is rotating at speed ns, and as the rotor magnets are also rotating along with it, the speed of the rotor is also going to be ns. So therefore the rotor rotates in synchronism with the rotating stator magnetic field. So this is basically the basic concept, the principle by which the synchronous motor operates. So now the question is, we know how to generate the rotating magnetic field. That is, in the stator, we have the stator like this. So let me represent the stator as this two rings of concentric circles, hopefully concentric circles, and we have the rotor. Let us still continue with this salient pole type of rotor. It gives the concept very nicely. So this is the rotor rotating about this central. Now, as far as the stator is concerned, we provide the three-phase AC source, the A, B and C, from a three-phase AC source or three-phase AC mains. So moment you provide such a three-phase AC source, current flows through the stator coils, which are spaced 120 degrees mechanical apart with respect to each other, and a rotating magnetic field of speed ns is equal to 120 F by P is produced. Now what remains is that the rotor should be a magnet also. So how do we make it a magnet? So that is by the principle of electromagnetic. You wind coils on the rotor, let us say. So let us say the rotor is wound with these coils. As shown here, and let me bring that coils out. Now here we supply a DC voltage. So if I supply a DC voltage, there is going to be a current I that flows, and we will call that one as I field. A current I field or IF flows through the coils as shown, and this is going to result in a field direction like this, which is equivalent to saying that this is north and south pole. So this, for this particular rotor, this north and south poles are fixed because the voltage here is a DC voltage. Now the rotor is rotating. How do we get this DC voltage to inside the rotor? So what we need to do is generate a DC voltage. So this is normally generated by a very small DC generator which is mounted onto the shaft of the rotor. So let us place a small DC generator So this is a DC generator. It has brushes, and then that is connected to the shaft of the rotor, mounted onto the shaft of the same rotor. So as the rotor is rotating, the shaft of the DC generator also is rotating. As this rotates, this is also going to rotate, and this is going to produce a voltage E, by the DC generator action, Faraday's laws of electromagnetics, and this voltage is going to drive a field current through the coils of the rotor, which is going to magnetize the rotor, the silent pole rotor here. This is generally how the magnetization of the rotor is done. Now there is one question that will arise now. At the time of starting, the rotor is not moving. And the rotor is not moving, the shaft of the DC generator is not moving. So the shaft of the DC generator is not moving, there is no E, and therefore there is no IF, which is not going to energize the rotor and produce the rotor fields. How will the synchronous motor start in such a case? So what is done is to have a squirrel cage on the rotor. That is, let us have a squirrel cage on the rotor as shown here. Let us have the squirrel cage as on the rotor as shown here. And this squirrel cage rotor can start by itself. The moment you switch on the power, this whole machine is going to start as an induction motor, and the rotor is going to come as close to the synchronous speed as possible, just within the slip distance, which means the shaft of the DC generator, which is connected to the rotor, is now rotating at almost the synchronous speed, just by a distance of slip distance, that is, it is lesser by an amount equivalent to the slip. Now this generates a voltage E. Now once the machine has picked up like an induction motor and come almost close to its full speed, the excitation of the DC generator is cut in by a centrifugal switch, let us say. So that gets cut in, and that is going to allow the flow of current into the coils of the rotor, and that will magnetize the rotor. Once the rotor gets magnetized, then the rotor locks onto the rotating magnetic field, which is rotating at synchronism. So you have the rotating magnetic field with a north and a south, and the moment the generator excitation, the generator induced voltage has built up, the current, excitation current flows through the rotor coils. This starts having the magnetic property, the rotor start having the magnetic property, it will have its north and south pole, and that will lock onto the rotating magnetic field and then always rotate in synchronism from there onwards. Okay. So that is how the synchronous motor is also started. So if you look at the entire synchronous machine, it has a shaft. So let us show the rotor shaft like that. So this is the rotor shaft. So on the rotor shaft, let us have the rotor. Let us have the rotor like that, and we have the stator, which is shown in green. This is the cross section. And on the shaft, we have a small DC generator. The electrical output of this is given to the windings of the rotor. As both are rotating the same shaft, there is no relative movement between the two, and the stator is provided with three-phase AC source, A, B, C. So this is a synchronous machine. This is a synchronous machine. So the rotor also has squirrel cage bar, and they are used for starting up the synchronous motor, bring it close to synchronism, and then the DC generator provides the excitation which magnetizes the rotor and makes the rotor to lock on to the rotating magnetic field. From there on, the rotor rotates in synchronism with the rotating magnetic field. So now the rotation of the rotor is in synchronism with the rotating magnetic field, and the rotating magnetic field is given by, as we saw in the case of the induction motor, 120 Fs by P, the number of poles per phase, or you could say 60 Fs by Pp, the number of pole pairs, or you could say it is omega S by Pp, the number of pole pairs, or which is equal to 2 omega S by P, where P is the number of poles. Okay. So this is number of poles per phase. Pp is number of pole pairs, north and south together, per phase. So this value will always be number of poles divided by 2. Pp is always number of poles divided by 2. Okay. So this is the speed equation for the synchronous machine, the synchronous motor. So now let us come to another important point, which is the back EMF. So let us say we have the AC source represented as a square block, and then we have the synchronous motor with the shaft rotating at synchronous speed. Now this synchronous motor, for the rotor, is getting an excitation from an excitation coil, which is provided by the output of a DC generator like this. So this DC generator is going to provide an output which is E. Now this E is going to allow, EG we will say, is going to provide the field excitation EF. This is the DC gen. Now the IF is going to magnetize the rotor, which is going to cause this to rotate, and there will be a back EMF like any generator action, and that is EB. And between the source, we are representing like a single phase equivalent. Between the source and the motor, there will be an equivalent reactance. Of course, there will also be the resistance, which is the winding resistance of the stator coils. However, the reactance X is so large compared to the winding resistance. In this case, we can neglect the winding resistance for the purpose of the discussion, because we want to get the concepts right. So we will call this reactance as XS, and that is called the synchronous reactance. The synchronous reactance. So at this point, you note that as the shaft is rotating at ns, ns is constant once fs is fixed, because p is fixed for the machine. So ns, the synchronous speed, is constant, which means the generator shaft is rotating at a constant speed, which means the induced EMF EF, the field EMF, is constant. Therefore, IF can be constant value there. Now, the source voltage, we shall call it as E. The voltage which is generated as a back EMF is EB, and there is a current, and we will call that one as IX. This is the current IX which is flowing through the synchronous machine, or we'll just call it as a current I. Doesn't make much difference there, because that is the only current which is flowing into the stator. So E into I will be the apparent power, of course. Now for this, let us draw the phasor relationship or the phasor diagram. So let me first copy this to the next page. So we have a copy of that. Let us make some more space here, and let us now take E as the reference. E is the supply voltage which is applied. Now the back EMF, there is a reactance coming into the picture. So the back EMF will also have the same amplitude of E, same effective value of E, because there is not going to be any power dissipated in excess. But EB will be delayed, it will lag the supply voltage E. Now of course EB is going to be proportional to the speed ns of the shaft and the flux phi inside. Now the speed ns is actually the rotor speed, and if I represent the red arrow as the stator and the blue dumbbell as the rotor, so if the stator field is rotating, the rotor also rotates, and both are rotating in synchronism. Therefore, EB will be along E, because EB is going to rotate as E is the source. EB will also be along the same value as E. So we will put value E across this under the condition when there is no current. So if I is equal to 0, then there is no drop across this. Therefore, E and EB will be along the same line. And exactly the same point, which I am going to show as this. So this would be E comma EB when I is equal to 0, that is no load. Now let us make EB small. Let us make EB smaller than E. How do we make EB smaller than E? We have it being proportional to NS. NS can't be touched because NS is fixed. The only thing that we can do is decrease phi. So EB can be decreased by decreasing the flux phi, which means by decreasing the current. This is obtained by decreasing IF. So what will happen under such condition? We have E and EB is going to be lesser than E. And now what is the drop across the excess synchronous reactance? It is E minus EB. So E minus EB is going to be E minus EB. This is across the synchronous reactance. Now as it is reactance inductive, the current has to lag the voltage across the reactance by 90 degrees. And therefore I has to be like that. This is I by 90 degrees. And now let us say if EB is increased beyond E by increasing phi, which is obtained by increasing IF. What do we obtain? We now obtain a situation. We'll go to the next page. We have E. EB is now higher than E. And what is the voltage across the synchronous reactance? E minus EB. E minus EB is going to be in the other direction like that. This is going to be E minus EB. Now the voltage across the synchronous reactance is going to lead the current by 90 degrees. Our current has to lag this voltage by 90 degrees, and that will be the direction of I. This is 90 degrees. So we have now three nice situations. First situation is we have E and EB, current is 0 I. This is no load. Second situation, we have E and EB is lesser, and what is happening to the current? Current is lagging by 90 degrees. And we have the third situation where we have E and EB is more than E, and as a result E minus EB is negative and the current is giving like that. So with respect to E, that is the input voltage. So if you compare the input voltage and input currents, input voltage and input current, you see that here the input current is lagging the input voltage. The input current is leading the input voltage. By adjusting the value of EB anywhere in between these 2 points, we can get different lead and lag angles of the input current. This means that we can adjust the power factor of the machine by adjusting EB or by adjusting the field excitation IF. Okay, so this is a very powerful feature which makes the synchronous motor to compensate for the power factor, lagging power factors of other loads. And that is why the synchronous motor is also called a synchronous capacitor. In where in industrial loads, where there are large industrial loads with lagging power factor, a synchronous motor is put with just no load and it is connected to the mains, and the excitation of the synchronous motor is so controlled such that the EB is at such a position that it compensates for the lagging power factor of the load, and the overall the AC supply can be made to see just unity power factor by means of this synchronous motor. So the synchronous motor can act like a capacitor which provides the reactive energy to the load, that is the downstream load, which is lagging in nature. Therefore the mains is presented with as though a unity power factor. Therefore the synchronous motor is also called a synchronous capacitor if it is used in such applications. When you load the synchronous machine, and if I take this to be the stator rotating magnetic field of the stator, and if we take this as the rotor, this is the rotor. Under no load conditions, both are together and then they are going to rotate in synchronism. But when you load, the rotor will lag the stator field by some amount, by an angle called delta, called the load angle. This is called the load angle or torque angle. However, both are still going to keep rotating at synchronism. So this is under load. This is under no load. This is the rotor. Blue is the rotor. This is the stator magnetic field. Stator rotating magnetic field. So under this condition, as the, let us say the stator conductor as a reference, this is the stator conductor. Stator conductor. The stator rotating magnetic field comes and cuts first, and then after some time the rotor field, that is, it also has its north and south pole, is going and coming and cutting the stator conductor after a lag, and therefore the back EMF will peak after the source voltage E has peaked, and therefore there will be a lag, electrical lag between the source voltage E and the back EMF EB induced, and therefore under such conditions, under load, if E were the source voltage, okay, the same amplitude, the back EMF will also be of the same amplitude, but it will lag by some angle which is proportional to delta, called the load angle, equivalent low electrical angle of the load. Now, what is this? This is E minus EB. This is the voltage across the synchronous reactance, and that I am writing it parallel here. This is E minus EB, and the current is going to be just directly orthogonal with respect to, so this is I, which is 90 degrees lagging E minus EB, and this is going to be, theta is going to be the power factor angle, PF, or the power factor angle theta. So we see that major portion of the active power goes on to the shaft, and the power factor angle can be controlled by controlling the amplitude of EB here. So by controlling the amplitude of EB, so let us say if we make EB more, that is if this is made like that. So you will have E minus EB like that, which means E minus EB is like that, and you can have a current just 90 degrees. So the current can either lead or lag depending upon the field excitation. This is proportional to IF. So as you control IF, you can make the input current lead or lag. So that is one of the major advantages of the synchronous motor. So the synchronous generator acts exactly like the synchronous motor, only the power is taken from the mechanical side and then the output is taken from the electrical side. So a prime mover will be moving the motor on the mechanical side, in the case of the synchronous generator. In the case of the synchronous generator, we have the synchronous motor, and let us say we have the shaft, and that is connected to a prime mover. So when the prime mover moves, there is of course on the DC gen. So DC gen is going to give the excitation for the rotor coils. So this is IF. Let me make some space here. So the DC generator is going to produce IF, which is going to energize the rotor inside within, and that is the rotor. So the rotor becomes permanent magnet, and that is rotating, and because it is rotating, it is inducing the voltage on the stator conductor, on the stator coils by the Faraday's principle, which is ND5 by dt, and that is being used to supply the electrical loads on the stator side, the three-phase electrical loads. And under such conditions, this is called the alternator. And the frequency of the wave shape here is always Ns. Is equal to 120 Fs by P, and therefore Fs is equal to P into Ns by 120. So the frequency of the supply here is always equal to Fs, which is Pn by 120. Okay. Otherwise, all other concepts of the generator, synchronous generator, is similar to the synchronous motor, and here also by excitation control you can control the amount of active power that is being put onto the load. So with this we shall conclude the synchronous machine. We just had a very brief insight into the synchronous machine, but along the lines of the induction motor, the induction machine, one could also develop the equivalent circuit and try to model it in greater detail. However, for the syllabus of the basics of the electrical technology, the scope for the synchronous generator is just enough if you get the basic concepts right. We shall now focus our attention on some of the projects that we can do with what we have learned till now. What have we learned till now is the basics of electrical technology and various equipments which are based on the basics. So if you recall, right from the beginning, we started the discussion on the sources, the various components, and then followed it up by modeling issues, and then the power factor issue, the phasor diagrams, and then finally we started discussing on the equipments and the machines. So we started with the discussion on equipments with the DC machine, the DC generator and the DC motor, and followed it up with the transformer discussion on the transformer, and then three-phase transformers, following it up with the most popular rotating machine, which is the induction machine, and it being acting as a generator, and then the synchronous machine. Today we got a brief glimpse of it. So let us see, or let us list down and discuss what we can do as projects in the undergraduate class with this particular background. So if I recall and list down some of the projects that we could think of related to these major categories. One is the DC machines, and second is the transformers, and third is the induction machine. So one can think of a lot of these projects on these directions, and of course the fourth one, a simple project on a synchronous machine. Now if we take the DC machine itself, one of the important interesting projects would be speed control of DC motor. Now the speed control of the DC motor can have various applications, like it can also be fitted onto a small two-wheeler and used as torque control, for, let us say, driving a two-wheeler vehicle. Then in the case of the transformer, we can have a nice interesting application. That is, we take single phase transformers, generate two-phase sources from three-phase input source and drive a single phase induction motor or an AC motor. That would be an interesting application. In the case of induction machine, one of the most popular applications would of course be simple stator voltage speed control. You can have a V by F speed control, and also more advanced control techniques like the vector control and things like that one, which we need not cover at this point of time because it's beyond the scope. And as far as the synchronous machine is concerned, a very nice and simple experiment that one could do is as power factor improvement by excitation control of the synchronous motor such that it acts like a synchronous capacitor. Okay. So these are some of the very interesting example projects that one could do as part of their undergraduate study or undergraduate curriculum. So let us see what is speed control of the DC motor. So when we take up the speed control of DC motor, speed control of DC motor, I will also include speed and torque control of the DC motor here. We have the DC machine. It has the shaft connected to the load. So we have the brushes here, and the brushes brought out as electrical terminals available here. So we know that the speed here can be controlled by adjusting the torque, of course. Now the torque here on the mechanical side is proportional to Ia, that is on the electrical side. The torque, the effort is proportional to the flow on the electrical side, and we have the back EMF here, EB, which is of course proportional to the speed omega on the mechanical side. So if we control Ia, we can control the torque, and for a given load the speed is going to change depending upon the amount of torque that you are going to produce. And this means that we need to have a variable DC source at the input. So if you vary this source here, Ia is going to vary, which is going to vary the torque, which is going to vary the speed, therefore EB is going to. Now how do we produce a variable source? So that is produced by having a DC to DC converter, which is having pulse width modulation, and that is going to produce a variable DC source which can be connected across the motor terminals. The voltage here can be adjusted depending upon the torque that you will need. So if we have, let us say, a reference torque, let us say, plus and minus, compare it with the feedback torque, compare it with torque fed back, and that is obtained as a function of Ia, isn't it? Torque per fed back is proportional to Ia. So if you sense Ia, process it electronically and bring it back, and that would be, and when you compare it plus and minus, you get an error E, and that error is passed through a controller, let us say a PI controller, and that would be used for producing a pulse width modulation. So as the current here increases beyond the reference torque, so you have the torque applied more than the reference torque, error is negative, the pulse width modulation reduces the voltage, reduces the current. So that would be the torque control. Over and above that, we can also have a speed control by measuring the speed of the DC machine by a tacho, or the voltage across the brushes, which gives you the back EMF. And if you have a speed reference, let's say N ref, and the speed feedback, which is proportional to actually EB, which is measured, which can be measured, again you compare, and the error is passed through another PI control, and that output of the PI control becomes the torque reference, and now that becomes a speed control of the induction motor. So you have the inner torque control loop, which is faster, and the outer speed control loop, which is slightly slower. Okay. This would be an interesting BE or undergraduate project. The next one, as I was saying, you could place the transformers, a single phase transformer, that is 3-phase to 2-phase conversion. So we have A, B, C. We have the A phase connected to a single phase transformer. We have the B phase connected to the transformer. The C phase is brought out. Let us say we have the center tap. Okay. Then we take the center tap, this is one output, and then across here we take another output with proper turns ratio 0.86 times as we discussed in the class. Now these two, let's say E alpha and E beta, are orthogonal. That is, you will have E alpha and E beta like that, E alpha and E beta, and this can be applied to a single phase motor, single phase induction motor, with the windings, the orthogonal windings brought out, and it can be made to run a single phase induction motor like that. That would be another interesting application. A third application would be an induction motor. An induction motor is operated as a generator. The induction motor is operated as a generator. So let us have the prime mover on this side coupled to the prime mover. Okay, so you have the flow of energy on this side, and then we have the three phase output power. Let us have the delta connected capacitance bank as shown here, which will supply the reactive energy to maintain the field, and let this go to a three phase load as shown. So driving the induction motor with respect to a prime mover, you can supply three phase load like a simple in the case of simple household or community lighting system, where the loads are properly distributed to get a balanced load system. This is an induction motor. And then we had discussed the speed control of the induction motor. Control of induction motor. So one can use auto transformers. An auto transformer is nothing like the transformer. You have just the transformer primary, and then you tap at various points with a tap which is connected to a rotary arm, so that you can tap along the various points of the windings of the primary and get any voltage which can be taken out of that one. And using the auto transformer, the stator of the induction motor, using a three phase auto transformer, let us say you have something like that, you have something like that, and you have something like this. All these are connected like that, and this is okay. So these are the windings. And you can tap equidistance from all the things and give it to the induction motor, and you can do stator voltage control. One could also do a V by F control by introducing some electronics. That is, you have an induction motor. The three phase induction motor is driven not directly from the source, but a three phase inverter. This is an inverter which is getting DC from a capacitance bus. You have a rectifier, three phase rectifier, and a three phase source. So a three phase AC source gets rectified DC, passes through an inverter, and then you have an induction motor. And to this you have a pulse width modulator, where you can modulate both the amplitude and the frequency that is applied to the motor. This will see that you have variable E and variable F. So if we are able to vary E and F in proportion such that we keep E by F constant, equal to constant, then the induction motor will be running in V by F mode, whereby you can utilize the whole range, speed range, right from close to 0 to up to base speed and beyond base speed with field weakening. So that would be the speed control of the induction motor. And finally, the interesting project is with the synchronous motor, where you have let us say a variable resistance here, and this is a synchronous motor, and you have the field excitation for the motor with stator supplied here. So this would be E, and what you have, the back EMF would be EB. Now EB is proportional to IF. So by controlling IF, by controlling this resistance, you can adjust the power factor between you can adjust the power factor angle between E and the input current I, and keep adjusting IF such that E and I are in phase, so that the main sees a unity power factor, whatever may be the load across it. So this would be another interesting application of the synchronous motor. So with this, let us conclude this session. Thank you very much.